welcome to numerical ship and offshore hydrodynamics. Today is the lecture 13. Today we are going to discuss a very interesting concept which is called the distribution of the singularities, and I will tell you this is the one of the most important aspect of this numerical ship and offshore hydrodynamics. So, before we start the boundary element method, we have to understand this concept. Okay. So, this is the keywords that we are going to use to get this lecture. Now, let us comes back to this topic. Now, it is very well known thing, right? It is a flow past a cylinder, and in your basic hydrodynamics you have this two dimensional problem, you solved it. Using potential theory, if you are going to solve this problem, how you solve this? Basically, you are really not putting any cylinder there, right. Here you have the cylinder, but you really do not put any cylinder here, physical cylinder. What you do? You have replaced this cylinder by distribution of a dipole or doublet, right. So, how we solve this problem? Let us have a look. Okay. So, now the problem is as follows. I have a cylinder like this, and then we have some flow, and we try to find out what is the mathematical model for this that flow past the cylinder. Now, we assume that there is a uniform flow, and this it is u meter per second, some flow is coming here, and then we need to find out that what would be the flow pattern, how we get the pressure, etcetera, right. Well, now here, because we are going to discuss some concept, we really do not discuss the mathematics, the important mathematics behind this. We assume that it is everybody. So, we start with a complex potential W z equal to u z plus mu by z. Now, this is how actually we can find out the flow past a two dimensional body in complex domain, right. Now, what is this? This u z is a complex potential for a uniform flow, and mu by z is basically the complex potential for a doublet with a strength mu, right. Now, if it is unknown to somebody, so just for them very briefly I will tell that any flow can be defined in terms of a complex potential, and there is the real part which is u x y, and then we have a complex part, let us say it is v x y. Under the potential theory, we can say that this W z can be written as the velocity potential phi x y plus a stream function psi x y. Not only that, if you differentiate with respect to z, and dw dz becomes that u minus I into v, where u is basically the velocity along x direction, and v is nothing but the velocity along y direction. So, this concept is very well known. So, therefore, we are not really discuss this concept. Let us try to find out using this concept how I can find the flow past a cylinder. Okay. Now, if W z equal to some u z, which is the velocity potential or complex potential for uniform flow, it is not subscript z, it is u into z plus some mu by z. Now, this mu basically nothing but the, let us say, strength of the dipole or doublet. Now, if you do dw dz, then you get, it is nothing but u minus mu divided by z square. Now, you know that dw dz is nothing but your u minus I v, the velocity along x direction and also the velocity along y direction. So, this you can replace by u minus I v is equal to this capital U, which is the uniform stream, minus mu divided by z square. Now, let us try to find out the stagnation point. What is the stagnation point? At that, suppose it is a the cylindrical surface. So, where the velocity is equals to 0. Okay. So, there is no velocity in u direction, there is no velocity in the v direction. So, essentially that dw dz should be equal to 0, right. Now, if I do that, if I make dw dz equal to 0, essentially what we get is u minus mu divided by z square equal to 0. Now, if I solve this, I will get mu by z square equal to u, and then I get that z square is equal to mu divided by u, and which implies, now z square is nothing but x square plus y square equal to u by mu by u. Now, this is nothing but the the circle, then x square plus y square must be equal to the radius. So, if the radius of the cylinder is a, suppose we assume the radius of the cylinder this equals to a. So, I can find out that there is a relationship between the radius of cylinder and the strength, right. So, it becomes a square equal to mu divided by u. From here I can find out your mu equal to u into s square. Now, you see it is very important results. So, actually what we achieve from here, let us see from the physical point of view. Now, I said I have a cylinder and then I have a uniform flow which is u meter per second. Now, if you give me the problem is that to find out that flow past this cylinder, I have to put a velocity potential for the uniform flow which is u z. Along with that, I have to put a cylinder a doublet or dipole with radius is mu by z, and then I found this mu is nothing but your a square into u. So, what I get is that initially I have a cylinder, right. Now, I want to find out the flow past the cylinder. So, what I do? Actually, I remove the cylinder, I remove the physical cylinder, instead I put at the center a dipole or a doublet with a strength s square u, and if when we put that, I assume that it actually physically represent flow past the cylinder where the radius of the cylinder is a. You see, it means that if I try to find out flow past a cylinder of some radius a, b, c, whatever, then I have to first find out what is the strength of the doublet, and you see that this strength of the doublet mu is somehow related to the geometric parameter which is the radius of cylinder. Now, in case of a cylinder it is very easy. Now, suppose if I try to apply the same logic for a ship, what is that? Suppose instead of this cylinder I put a ship over here and I try to find out the pressure distribution along this hull, right. So, idea is, in case of a cylinder, I put a doublet at the centroid of the cylinder or center of the cylinder with a strength mu equal to S square into u, where both is known to me. So, if I try to find out the pressure field along this hull, then what would be the distribution, right? Is it a source or is it a dipole or is a combination of both? I do not know. Also, I do not know what would be the strength of the source, what would be the strength of the dipole. See, now you see I am actually in numerical sheaf hydrodynamics, we are actually solving the similar type of problem, but now problem is more complex, right. In case of a 2-dimensional cylinder, I know everything. I know the this abstract doublet, the strength of this abstract doublet mu, I know it is related to the geometry of the cylinder, right. So, it is for me it is very easy, you can tell me that find out the let us say there is u equal to 4 meter per second, okay. And then you find out, let us say, the radius of the cylinder A, and that equal to, let us say, some 10 meter, and then you ask me find out, I try to find out the pressure pattern along this cylinder. I say it is very easy, because my gamma is related to both. So, gamma is nothing but u into a square. So, if I put this strength, then definitely I can get what you are asking for, right. So, this is the idea, this is the basic idea of the distribution of the singularities. Why I call this singularities? Because you can see here it is mu by z. So, at z equal to 0, this function is a singular, because its functions become infinity, right. So, here for this particular problem, I distribute the singularity at centroid with a strength, which is I relate this strength with my geometry. So, given a geometry, I understand from this particular problem, given a geometry, I really can find out a strength, and then I can solve the problem. I only need to know two things, like how I can distribute the source or distribute the singularities dipole, and also second point is how to estimate the strength. Clear? Okay. Getting this idea, so getting this idea, let us move on with the Green's function and then distribution of the singularities. Now, here we are going to use this integral, I mean this Green's theorem. It tells you, let us say, phi and psi be any function. So, there are other mathematical definitions, for at this moment let us ignore it. Here it says that this is a volume integral, you can see from the left hand side you have a volume integral. So, volume integral phi into del square psi. So, it is a Laplacian, right. Here this is a so here this is a Laplacian, right. So, phi, I mean del square psi is Laplacian, del square phi is a Laplacian, right, and then this equals to the right hand side, which is phi del psi del n minus psi del phi del n. I am going to use this result, okay. I am going to use this result to find out something. Let us see. Now, before we proceed further, try to find out a simple thing, that the what is the meaning of a velocity potential. So, we can call the phi is a velocity potential if del square phi equal to 0, right. This is how actually we say that whether this function is a velocity potential or not, right. Suppose if I given you a function, let us say phi x y equal to y square minus x square, and if you ask you if somebody asks you like whether it is a function of velocity potential or not. So, first thing what you do, you find out del square phi by del x square plus del square phi by del y square, which is this equal to 0 or not. In that case, it is 0. So, we can call this function is a velocity potential. Fine. So, now first let us try to find out whether this phi 1 upon r, I mean this phi, okay, this phi, this function is 1 upon r, whether this function is a velocity potential or not. Okay. And the definition of r is nothing but x I plus y j plus z k, and therefore, this r square equal to nothing but x square plus y square plus z square, right. So, now before we proceed further to check whether this del square into 1 upon r this equal to 0 or not, okay, let us try to find out little bit some manipulation. So, I just differentiate with respect to x, we get 2 r into del r del x is equal to 2 x, which implies del r del x equal to x by r. So, similarly, I can find out del r del y equal to y by r, and similarly del r del z is equal to z by r. We need to remember these results, and then let us try to find out what is the grad of 1 upon r. Now, I know the definition of grad is as follows, it is I into del x plus j into del y plus k into del z, and now it is into 1 upon r, right. So, I have I into del x of 1 upon r plus j into del y of 1 upon r, and then I take k of del z of 1 upon r, right. Now, you know the chain rule. So, it should be I into del r by 1 upon r into del r del x plus j into del r into 1 upon r into del r del y plus k into del r upon 1 upon r into del r del z. Now, if you substitute everything, see, you know, del r 1 upon r is minus 1 upon r square, at del r del x if I use the x by r. So, I will get it is minus, you know, I into x divided by r cube plus j into minus y divided by r cube plus k into minus z divided by r cube. Okay. So, I just make here also similar minus I. So, I just replace this as this way. Okay. So, I get that grad of 1 upon r is equal to I into minus x by r cube plus j into minus 1 upon r cube plus k into minus z upon r cube. So, del square 1 upon r nothing but grad of 1 upon r. So, it is again I just apply over here, let us quickly apply this, it is I del x plus j del y plus k del z. So, these are definition of this, and now I just find out is nothing but dot product I into minus x by r cube plus j into minus y by r cube and then plus k into minus z by r cube. So, if I use the dot product, it is simple. So, then I get it is del x of minus x by r cube plus del y of minus y by r cube and plus del z of minus z by r cube. Now, you know this how to do this. So, it is u v function, if you can break it. So, del x, so it is become like minus 1 upon r cube and then minus x into del x of 1 upon r. Similarly, second one is minus 1 upon r cube and minus it is y into del y of sorry, it is r cube, it is 1 upon r cube and then it is third term is minus 1 upon r cube minus z into del z of minus, not minus, it is 1 upon r cube. So, this is something that you are going to see, and then now if you do this, I will get here minus 3 by r cube coming from here, and if you do here. So, again I know that I should write x into del r of, I just doing for 1, okay. It is 1 upon r cube into del r del x. So, I just part from this. So, I just get minus 3 by r cube and here I will get plus 3 into x square divided by r to the power 5. Similarly, if I part from this, I will get plus 3 y square by r to the power 5, and if I part from this, I will get 3 z square by r to the power 5. So, you can do by your own, you can check that, and then finally interestingly what I get is del square 1 upon r, this equals to minus 3 by r cube and then plus, if I take common 3 into x square plus y square plus z square divided by r to the power 5. Now, this equals to r square. So, I will get a nice fine minus 3 by r cube plus 3 by r cube. Now, you see the interesting part is this equals to 0 if r not equal to 0, else when r equal to 0 this function goes to infinity. So, it is a singular function. So, what I get? I get a nice thing that this function phi is equal to 1 upon r, it satisfy del square 1 upon r everywhere apart from origin, that means at r equal to 0. So, we can say that this is basically a Laplacian everywhere apart from the origin, and then it basically it is at that particular point of time it is a singular function. Okay. Now, this is a very powerful function for us. Why it is so powerful? Let us try to figure out. Now, again as I said, I am going to use that particular boundary integral method, like that Green's identity, which is if I apply over a volume phi into del square psi minus psi into del square phi dV. Now, it become a surface integral, as you know, it is S into phi into del psi del n minus psi into del phi del n into ds. So, this is my result. Now, what I do is, let us find out a domain, a circular domain like this, and let us take a origin over here and then I just cut this origin with a small circle, and then I make this two surface. One is, so this is my volume V, this is my volume V, and this surface, outer surface, call it S, and inner surface let us call is a S epsilon, which is very tiny surface, very small surface, right, which basically only capturing the, just deleting that singular point. Now, if I take the phi is basically my velocity potential, and if I take psi equal to that function 1 upon r. So, then psi also satisfy the Laplace equation, because I am cut out this one I cut. So, in this domain, so this entire thing, this del square phi should be go to 0, and then del square psi also 0. So, entire left hand side is 0. So, it is 0, and then in the right hand side what we have is that we have a surface integral S plus S epsilon with phi into del n of 1 upon r minus 1 upon r into del phi del n ds. In fact, I can call ds plus d epsilon, right. And then what I could get is, I can find out this S into phi del n of 1 upon r. Okay, let us take, instead of phi, let us say 1 upon 4 pi r. Okay. So, I just take psi equal to 1 upon 4 pi into this one. Okay. So, this minus 1 upon r del phi del n. What I do is, so this S, I split S equal, I mean S plus S epsilon. So, then I just add another one, it is on S epsilon and the same thing, right. So, ds epsilon, that should be equal to 0, right. So, I take this in the right hand side. So, then I get S phi into del n of 1 upon r. So, I just write 1 upon 4 pi here, because I just take psi is 1 upon 4 pi r, right, minus 1 upon r del phi del n ds is equal to minus 1 upon 4 pi. Now, I have over this S epsilon, I take this right hand side, this phi into del n of 1 upon r minus 1 upon r into del phi del n into ds epsilon. Now, remember my domain is circular domain here, this one. One important thing to note is, if the outer the normal is positive here n, so it should be the, here it should be the minus n. Why? Because you can see here the direction got changed. So, here it is coming here, and then here it is anti-clockwise, then here it is clockwise. So, the direction of the n should change. So, if the S in the surface of F, which is the positive normal, the same normal at epsilon become the negative normal. So, that one thing we need to remember. Now, here we can say it is basically I 1 plus I 2. Now, this I 1 equal to integration of S epsilon phi into del n of 1 upon r. So, minus 1 upon 4 pi is there, of course, ds epsilon. Now, since this epsilon is very small, we can assume the whole contribution lying on the centroid. So, I can think that phi is a constant. So, I take out the phi outside. So, I become phi by 4 pi, and then this S infinity is simply del n of 1 upon r into d epsilon. Now, in case of this small circle, the area is nothing but, surface area is 4 pi into r square, right. and then del n of 1 upon r. So, now it is a circle. So, my normal definitely for outer side if it is del r, then for the inner circle it is minus del r, right. It is very easy because so this is the radial direction definitely normal to this surface, right. So, this inner circle it is minus del r. So, I replace this equal to minus phi by 4 pi. Now, here it is minus del r. So, it is minus of now del r of 1 upon r equal to minus 1 upon r square. So, this minus and this minus we cancelled out. So, it has become 1 upon r square and then I multiply by the surface area which is 4 pi r square. So, this r square cancelled out, 4 pi cancelled out, this equals to minus of phi. Now, this second term I too eventually go to 0. Why? Because again the linear sense you can check that I have 1 upon r, this is my integral. If I multiply by 4 pi r square, so then actually it becomes order of r. Now, this goes to 0 as epsilon goes to 0. So, this is my argument. So, I can omit this, I can ignore this, I can make 0 and then I get a very nice expression, and my nice expression is as follows. I can get this phi at any point x, y, z if I distribute the singularity over the surface and if I know that what is the normal of the singular function 1 upon r minus 1 upon r and what is the normal velocity of this particle at this surface. Now, you see I can find out the velocity potential for wave, velocity potential for anything at any point in the fluid domain if I know the velocity potential at this surface and the normal potential also at that surface. See, it is a very interesting result. You see, I just take a domain, this is my fluid domain, as you know that I draw it and then you have a surface and you have a body over here. Now, everything, so here entire domain is phi. So, I can find out pressure at any point inside this fluid domain if I know the velocity potential lying on the surface and the normal velocity potential lying on the surface with the help of the singular function 1 upon r. And one more thing you see here that this 1 upon r it is classically known as source and 1 upon r is classically known as source. So, del n 1 upon r is known as dipole. So, we can say this is a source dipole distribution. See, coming back to again this the problem that is related to the flow past the cylinder. There you put a dipole at the centroid. Now, here we have to distribute the source, we have to distribute the dipole over the surface. So, therefore, I can see that this phi could be think of a strength of the dipole and then del phi del n can be thought of the strength of the source. See. So, you see everything is interrelated for the 2 dimensional flow plus the cylinder everything is fine, but here also the same concept I am applying to solve the 3 dimensional problem. Okay. So, now comes back here. So, this is basically the classical boundary integral equation that we are going to solve in coming days. Okay. So, with this, thank you.